Great. So now of course we'll know from your specifications you can find what is the omega u for the differential mode and your phase margin for your differential mode. Right. And similarly now you also see that we also have a negative feedback loop working separately for setting the common mode, and you can see here. So this is basically your common mode half circuit. This is also a two-stage OTA and this was also compensated. So this will have its own omega u and phase margin, right? So now we'll try to see what does it mean for a common mode feedback loop to have a particular omega u, right? What does it mean, right? So to understand that, I'll want to bring your attention to this circuit. Let's consider this differential amplifier. Right. So this is also a differential amplifier taking in two inputs and giving a differential output. But what is lacking here? The common mode rejection is not there, right? Because let us say if I go and apply a common mode input here, VIC and VIC, right? So if I draw the common mode half circuit, you'll just have this guy, PMOS and NMOS like this, right? And here I'll apply VIC, okay, and this is incremental shock. So now if I apply VIC, so let us say at the output I have a capacitance. So let us say VIC is a step like this, right? So what will happen to the output common mode small signal? Huh? I mean, I'm just, this is a circuit, right? I've applied a small step. I want to see what will happen to the output. Or what do you think will happen? Sorry? Yeah, I mean, so that's okay, but how do you, I mean, okay, if I apply a VIC as the small signal input, what is the small signal current being drawn here? GM times VIC. The current is a constant. You have a constant current being drawn out of this node, and that node has an effective capacitance and some resistance. So it's basically this, right? I have a current here being drawn out of this node which has an effective R out and let us say some CL. This is just now constant current GM VIC. So how will the output look like now? Capacitors, let us say, initially discharged. It's a first order RC circuit. So what will happen? Output will start, I mean, if I apply a sudden change, will the output change? So it will start from 0, and what will happen? In steady state, what will happen at least? In steady state, what do you think the output will be here? Sorry? Can you check carefully? It is partially correct. Minus. You are pulling current out. So in steady state, capacitor is open. So it's basically minus GM whatever, VIC times R out. But in transient, you will have an exponential settling like this. So you will set to this, what will happen? And this is obviously not great because you want your circuit only to respond to differential mode signals. But this guy doesn't differentiate between common mode or differential mode, because even if you draw the differential mode half circuit for this, you'll have the same guy, right? So the response to both differential and common mode signals will be identical. So this is bad. So now let us say I make a minor modification to this. So I take the same guy, I'll draw here. And by the way, remember, this is basically what we called as pseudo differential. It's differential circuit, but it does not have any common mode rejection as such. So it's typically called the pseudo differential circuit, right? So let us say I do another experiment. So I take the same circuit, but make one minor change. So here again, if I see the output DC bias, that will not be set, right? Because you once again have two current sources connected in series. So as such, if I put the circuit, it will not work. So this one is just a thought experiment wherein somehow I magically assume that the PMOS and the NMOS are biased, so that both currents are equal, and this voltage is set to a value so that all transistors are in saturation. This will not work in practice if you just put it, but just for demonstrating an example, I took this. Okay. Now in practice, to set the DC bias here, you need a common mode feedback. So let us say I put a common mode feedback here. So I sense the common mode using resistors, compare it to some reference, say some Vref, and let us say I go and tune the PMOS current. Okay. So now let us say I apply only DC bias for both inputs. What can you say about the output common mode or the output DC bias here? It will get fixed to Vref. That's what the loop is doing. Again, let's assume that this has infinite DC gain to begin with. So which means the loop will make sure that the difference here is 0. So which means the average or the output common mode here will get set to Vref. Okay. Now let us say I go and apply a small step change here like I did before. Okay. So again, let's draw the common mode half circuit to see the common mode response. So here if I draw this, I will have the same PMOS, the NMOS. Here is where I apply this step, and then I will have the two resistors being put in parallel. So I will have one copy of the resistor that goes to this, and let us say I am drawing the small signal, so supply is ground. This Vref is also small signal ground. Okay. So let's see, can I make something? Yeah. So the thing is, earlier let us say the bias voltage, the gate voltage was at VBN, and in that case I saw that the output was set to Vref, right? Now let us say at this instant the gate voltage jumps up by a small VIC. Okay. Now we are interested to see what will happen to the output. So now look at this circuit. This is the small signal equivalent for common mode behavior. Once again, let's assume that this has an infinite DC gain. So which means in steady state, what can you say about the common mode here, small signal common mode? Will be 0, right? Because again, this has infinite gain. It will make sure that these two voltages are the same, because this is put in negative feedback. This voltage and this voltage are the same because no current is drawn. So this will get set to 0. So which means there is going to be no incremental change in the output. So in steady state, what can you say about the total voltage? Yeah. It will be same as Vref. I mean, same thing, right? So it will eventually it will come to Vref. Right? Now if the OTA has an infinite speed, it will make sure that for all time instance it is always set at Vref. But of course that's not the case, because you have parasitic capacitors everywhere, say one here, one parasitic capacitors here, and inside the OTA itself you will have some poles and zeros. So things are not going to happen instantly, right? So first let's look at what will happen at t equal to 0 plus. That is just after I apply this step. At t equal to 0 plus, what can you say about the capacitors? How can I treat them? Loosely speaking, I can treat them like a short, right? So this is now short. Similarly, this capacitor is a short, and the this short I'll explicitly show. Oops. I'll explicitly show like this. Okay. So this is also short. So which means at t equal to 0 plus, what can you say about the output? Incrementally 0. So it will still remain at Vref. Okay. Now after t equal to 0 plus, let us say that the OTA is still not responding. So the gate voltage is still not changing. Okay. A small time just after t equal to 0 plus. Let's assume this is the scenario. Now if you see, these two circuits are same, right? because I've assumed that the OTA has not responded yet, so the gate voltage has not changed. So which means, what can I say to the output now? What will happen? It will decrease as before. And if the OTA was not there, it will basically go and settle to the same value as earlier, right? But now, let us say after this point, the OTA has started to respond. Okay. So now the OTA will make sure that this will eventually settle to this, right? Or I'll slightly exaggerate and show. It will do this, and then now what do you think will determine the speed with which this settles to? Omega u of this feedback loop. Again, this is a negative feedback system. The speed of that feedback system is determined by the omega u of this feedback loop, right? If this has a larger omega u, basically this might say settle faster like this. If not, it will take longer time. Now, in addition, if this feedback loop has a very poor phase margin, you might see a lot of ringing, okay, before it eventually settles. Okay. So that's what we mean when I say that my common mode feedback loop has some particular phase margin and a particular omega u. This is just the way, this will quantify the way in which your system will respond to common mode changes. Okay. Right. So now, as you can see, this common mode feedback loop, in addition to setting your output DC bias to some value, it is also making sure that if I have any common mode changes at the input, that kind of gets suppressed eventually, right? Because when I didn't have CMFB, the output was responding to the common mode, but the moment I have this, at least eventually the input, there is no response to the common mode input. Okay. So in addition to the common mode feedback loop, it also gives you some common mode rejection, right?
So those are pseudo differentials, right? If you have a fully differential, it's already.
Yeah, that's what we'll come to it. But this is okay in a pseudo differential also. Like I told, you can't leave it like this, because that is just, like it will not work like this, because you have to exactly make sure that this is at a particular voltage so that currents are equal. And even then, you should somehow make sure that the voltages here are reasonably good enough so that all transistors are in saturation, right? So even if you have a pseudo differential case, you'll end up having a CMFB, and that will provide some common mode rejection like this. Okay. And remember, this has nothing to do with your differential mode differential mode omega u and differential mode phase margin. Now this OTA, this is a fully differential OTA, right? So you might finally use it in a negative feedback loop like this, right? So let us say something like this. Finally, you might be interested to see if I apply a differential input, how the output will respond to this differentially. So the response from the differential input to the differential output, how fast things settle and stuff, that will be determined by the omega u and phase margin in your differential mode picture. But your CMFB's thing, that will say if there is any common mode jumps, how fast my loop will be able to suppress that common mode jump. That will be determined by the CMFB's omega u and phase margin. Okay. But like he asked, then this is, let us say now, if this is providing you some CMRR, the question that might come is, why do we even need to have this tail current source and have better CMRR, right? That's a reasonable question to ask. And for that, let's actually look at that also. What I'll do, I'll copy the same thing maybe to save time. This is point clear now, at least. The CMFB, if you put in a pseudo differential thing, that will provide some common mode rejection. But how fast it suppresses the common mode is dependent on the omega u of the feedback. Okay. So now let us say I take same thing, but I inherently give it a good common mode rejection by putting a tail current source like this. Right. So now once again I am applying doing the same experiment, applying a common mode jump. So let's draw the common mode half circuit. So if I draw the common mode half circuit, again I'll just draw, maybe one side I'll draw. This is the common mode half circuit, right? And let us say I'm drawing the small signal, so I'm applying only a small signal VIC here. This supply is incrementally short, and the current source here, that will be open. So now what can you say about the small signal current here? 0, because we have open. So if the small signal current is 0, what can you say about the small signal change? So which means in this case, let us say the output was initially at some VREF, and at this instance you go and applied a common mode jump. What can you say about the output? It will stay the same, right? Now of course the question is, of course you might ask us, will not have an ideal current source, so what will happen? So let us say the current source has a small signal resistance Rx. So in that case, what do you think the current is, small signal current, approximately? Can you give me a quick estimate of the current? Okay. Sorry? GM? No, but current is what? GM VG or GM VGS? VGS, right? See, let's assume that Rx is reasonably large. If let us say Rx is not infinity but a large enough value, then what can you say about this voltage approximately? Gate is VIC, Rx is a large enough resistor, so what is this voltage approximately? Approximately VIC. So if this voltage is approximately VIC, what can you say about the incremental current? So I mean, you can exactly work out what this is, but this is a good approximation as long as Rx is large enough, greater than 1 by Gm. Okay, and now we can see, right? I mean, if Rx is infinity, the current is 0. That's what we expected. If it is not the case, this current is still small, right? Now, if you compare with the earlier case, in this case, right? Oops. What's happening? Yeah. In this case, if I apply VIC, what can you say about the small signal current here? Gm times VIC. But here, in this case, the current is much smaller. Okay. So here also what will happen, because the current is not 0, when you apply a change in the input, you'll have a small change in the output. Okay. But the common mode feedback loop will kick in and immediately suppress it. Whereas if you didn't have this guy, if this was short, which means you didn't have this current source, then this would have basically gone to a large value. Okay, because the incremental current was much larger. Okay, so that is why it is not always a good option to rely on the common mode rejection provided by your CMFB. So it is not good to just rely on that. You start off, you have a good CMRR by having the tail current source. Right? Great. Now again, another perspective to look at the same thing is this, right? So let's see. Yeah. So in this case, pseudo differential case itself, let's take here, when I didn't have the CMFB, if I draw the half circuit for common mode or for the differential mode, it is the same. That is why it was responding the same way for both common mode and differential mode signals, right? So now here in the pseudo differential thing, when I have a CMFB, so let's quickly see how will be the two half circuits. So this is the thing. So here the common mode half circuit I already have, so let me copy that. So this is the common mode half circuit. So here let's draw the differential mode. So which means in the differential mode what I am applying is, say, some VID by 2 and minus VID by 2. So as usual, the middle voltages are all 0. So this guy is 0, this guy is 0. So this is basically the gate of the output of the OTA, that is also 0. So once again the OTA will not be in the picture. So you will just have basically 1/2 the resistor. Okay. So here again, if you want to find the small signal gain, we can do short circuit GM and R out, right? So in this differential mode half circuit, what can you say about the short circuit GM? I short the output and find the current. What do you think that is? The GM of that NMOS. So here what can you say about the short circuit GM? Let me actually erase the capacitors. Yeah. Here also if I short the output, what is the short circuit GM? GM of the NMOS. Here also it's the same, right? So the difference will come in which then? R out. So let's quickly see here. The R out is simple. What is the R out? The parallel resistance of the NMOS and PMOS parallel to the common mode resistor used. Let us say this is RCM. So here what is the, let's find the same. Here what is the output resistance? Okay, let's say looking down, what is the resistance here? Okay, so at least that should be clear. Looking down, it is the R0 of the NMOS. So what is the thing looking up, do you think? 1 by? Okay, so let's simplify it, right? So let us say this has a gain of some A, DC gain, right? So I can basically redraw this like this. I have the PMOS and then I am having a gain of A, something like this. Same thing, I have simplified it. Again, if you see, the resistor will not take any current, so that's not relevant at all. So here if you apply a test voltage, what will be the gate voltage here? So again this is incrementally short, so sorry, yeah. So here it is going to be A times V test. So what will be the incremental current? GM times? Fine. GM times VGS. So what is the output resistance then? 1 by AGM. Okay. GM of the PMOS. So this as good as having. So once again, now you see that if the gain is infinity, the output resistance is 0. So which means the common mode DC gain is 0, and that's what we also saw, right? The if I make any, this VIC, if I make a common mode input here, the output in steady state was 0, and that was happening because the common mode output resistance is actually 0. Now if the gain is not infinity, it is a large enough value, you will find that if I apply a common mode input, there will be a small response due to it, but it won't be exactly 0, but it will be small. Okay. So that's what happens. So when you have the common mode feedback loop, it kind of changes the output resistance in the common mode picture, so that the output resistance reduces in the common mode. Okay, great. So that's mainly about things on common mode feedback.